there's more value in the connections outside of these talks than actually listening to the talks themselves. Like, we've spoken to a lot of very experienced, very tenured people who have lots of, great stories and mistakes that we can learn from so that we don't have to make them as well.
Hello everyone, good afternoon. This is a talk about deducing this, which is a new C++ feature for C++23. I have adjusted the slides for the poor projectors in this room. I hope they work better today than yesterday. So, the feature is P0847, that's the paper number. I'm a co-author along with Gashper, Sai, and Barry. And what the feature is in a nutshell, this is the abstract, a new mechanism for specifying or deducing, that's important, you can do both, the value category of the expression a member function is invoked on. So the type of this, the type of the object, that implicit first object parameter. So whether it's null value or null value, whether it's constant or volatile, and its type. In this talk, I'm going to talk about just a bit of introduction about the history and motivation of this paper. Then we'll go over what the feature is. Then I'll show some existing patterns in code that we write today that are improved by this feature. And then some new patterns that aren't possible today and are possible with this feature. And then there's a bit of miscellanea at the end. Quite a lot to get through. Do please ask questions as we go. There's code on the slide. You should consider it exposition only, although for the most part, I have tested it in the Circle compiler, thanks to Sean. Another feature that Sean has implemented for us. So, first, the origin story. Here is how it sort of came about. So in 2013 or so, back in the day, I was playing around with monadic futures, and I run into this problem. I went to C++ Now in 2014, completely overwhelmed. I went back in 2015, and now I felt confident enough to tell people a bit about the problem and see what they thought. Time goes on. In 2017, I talked to Gashper, and I kind of nerd-sniped Gashper, and he got really interested in this problem. And then we found out, I think through David van der Voorde, that Sai and Barry were also working on the same problem. We all joined forces. 2018 was the first time the paper was presented, first at C++ Now, where a bunch of standards folks were in the room, and Gashper was currying favor with them at the time. June 2018, the paper was first presented to the standards committee for real. July 21, the paper was at revision 7, and just now, just in October 2021, the paper passed the plenary vote, and it's in C++23. So that tells you a bit about how long, and this is actually a very fast feature, I would say, to get into the language, but this tells you a little bit about how long that takes. So the problem I ran into was this. If I have, the original problem, if I have a callback, a Lambda expression, which becomes a closure object, and it has a captured value, how do I know whether I want to move the value out? How do I get that full kind of efficiency that I want? It might be just a one-shot, or it might be something that gets called multiple times. And in general, there is no way to know from within a Lambda what the value category of the closure object is. So this was my original problem. So firstly, when I went back to C++ Now in 2015, the response I mostly got from folks was, we have bigger fish to fry, and fair enough at the time. They were working on C++ 17. There are lots of things in C++ which could, get some attention, but anyway. The problem stayed in my mind. As I say, I nerd-sniped Gashper effectively at CppCon 2017 in Bellevue. So this was an interesting insight into working with the committee. Everyone who worked on library stuff was like, we want this like yesterday. Like this is going to make us take away so much code. We've got so many places to use it. And the language side folks said, well, we're not really sure we see the use case yet. This is kind of how it should be though, right? Because we should be parsimonious with language features, right? This is a healthy committee. Anyway, here is the feature. When you write a function, a member function, this is the variant of the feature where we're deducing this. It can be a template, and the first argument there is the implicit object argument, and it's prefixed with this. So by the end of this talk, you will understand what this slide means, and we'll go through examples, and I hope you'll get some ideas and get excited about it for your own code. I'll be conventionally using self as the type, capital S, and self as the name of the value, but you don't have to use self, and you can leave the value unnamed, just like regular functions. The parameter can be unnamed. So, here's what changed, and importantly, what didn't. The only thing that changes is this as an annotation on the first parameter only, that makes that implicit first argument, that object parameter, explicit on non-static member functions. And then very importantly, everything else pretty much goes unchanged. And this is important for standardization because if any of these things really did change a lot, we wouldn't be seeing this probably maybe ever. So we didn't change template deduction rules, we didn't change overload resolution, we hardly changed name lookup. There is one very small change inside functions that we did. This is still a pointer. C++ had this before it had references, so we can still be sad about that, but this is still a pointer when you say this. And another important thing, the meaning of this inside a lambda, because it has a special meaning inside the lambda, of course, that remains unchanged. So, the good thing about this feature is that you pretty much already know how it will work. It's a sort of thing that we added, but all the other rules of C++ that you know and love, or know and don't love so much, but still know, they can all be applied. So, as it turns out, C++ spent about 40 years hiding that first argument, this argument. Making it explicit turns out to be kind of good. So, yes, if you already know how it works, if there's a logical deduction from rules you already know, it's very probably how this works. So, just to introduce it, some quick equivalences. The top is what we write today. We've got value category specifiers, reference qualifiers on member functions. And the bottom is what we might write with this feature. And these are morally the same thing. In fact, you can still use either one in future, but don't define both because they are morally the same thing. It's an error to define both. So, there is one kind of first obvious win here, which is that it's a massive amount of deduplication or triplication or whatever. So, today, we write these functions. Well, maybe we write these functions. Usually we write const and non-const, and R value qualifiers, L value qualifiers. I was talking to Daisy earlier, and she did have occasion recently, I think, to write an R value volatile qualified member function. But mostly we don't do this, right? And mostly our programs are not complete because of it, and we pay some price sometimes. But when you write this, the compiler synthesizes all the kinds of member functions that you use, right? It's a template. And so this effectively means you get all of those for free, as we'll see, because it's a function template, a member function template, the compiler will synthesize those. Okay, so like I was saying, before this feature, P0847, we have several, if we actually want to do this, we have several fairly unpalatable choices. The most likely thing is that we neglect to write a bunch of overloads. We can write them all separately, or make them all delegate to one and have some kind of nastiness like const cast. Or we can delegate to a sort of free function template helper or another member function template helper. But all of these choices involve some amount of copy pasting. And for member functions before P0847, that's pretty much required. And of course, anytime there's copy pasting, there's the possibility of error. So with the deduplication with this feature, now one function template will do it all. This is a very simple example of a getter. We've got the this qualified, or the this marker in front of the regular forwarding reference of the object parameter. And we're going to, use perfect forwarding and get the member variable out of it. And this does it all. This is, the compiler synthesizes whatever of this that you use. So const qualified, L value, R value, volatile if necessary, etc. So the question of what to return here, I put decal type auto or see next slide, because there is a little recipe for the return type that may need to be employed. And it's this thing like T. And what like T does is a little meta function, if you need it, that basically applies the reference qualifiers, the top level CV qualifiers from the one type to the other type. So this is how it works by example. And with this recipe, you can write, as in this case, a single optimal template method, which will do the right thing for all of the reference categories, etc. So when S is a const ref, the getter will return a const ref to member. When S is an R value ref, the getter will return an R value ref, etc., etc. So immediately you can think of writing value wrappers like optional, and this hopefully immediately has a lot of value, all that deduplication. Now, as with like T, there is another sort of helper, which you might see coming up in slides. It's forward like. And this actually, happily, is in the mailing that just came out this week. A paper by Gashper, P2445. And forward like is exactly what you would think. It forwards the thing like the thing. So these two meta functions, like T and forward like, I present them here by example, but you can find them online. You can ask Gashper if you need them. But hopefully forward like is going to be in C++23 as well, hopefully. Gashper told me that I think it's pretty much had a favorable reading through LEWG already. Okay, so anyone have any questions at this point? As I say, Jody.
Yeah, so I think on slide 14, you have the template. Does that mean that, so up to now, special member functions are not templates? Does that mean the special member functions now can't be templates? It's just a special level command?
So up till now, special member functions are not templates. Does this mean that special member functions specifically can be templates?
Yeah.
I believe the answer is yes. Member functions and special member functions. There might be, I mean, I don't think, it doesn't make sense for constructors and destructors, but for other special member functions, I think the answer is yes. Okay. Oh, another question.
Actually, go back to that slide. In the function body, can you use both this and S?
In the function body, can you use both this and this? No, that is the one change to name lookup.
Okay.
And we'll get to that. So
okay.
In general, you cannot use this in the function body, and you cannot use implicit this. You can't just say names of members. right? But we'll get to that. Yeah, generally that's not a problem. The rule is like you named it, you use it. So, okay, where were we? Okay, so that was a simple win. This is an important slide to understand. Template deduction is unchanged. So we have a base class here with two functions. Func1 is not using deduction on this, it's just using constraint, right? And func2 is using deduction. And then we have a derived class. When we call through the base func1, we get type const base ref. And when we call func2, we get the deduce type, which in this case is base ref. When we call through the derived class, func1 still is a base ref, right? Still is const base ref. But func2 uses the deduction and it deduces the statically most derived type. So we get the derived L-value ref. This is very important because this turns out to be very powerful. Let me give you an example of how this is powerful by considering CRTP, the curiously recurring template pattern. Now, if we write this today, and this is from Jonathan Beccara's blog, Fluent CPP, we have this kind of pattern, right? And this static cast tref is sort of a characteristic incantation of CRTP, right? In the base class, we've got the derived class as a type parameter, and we do the static cast because we know it's derived. And the curiously recurring part is on the derived class, which inherits from the base of itself, right? This is CRTP today. With P0847, CRTP really just almost completely goes away because you can just write the function template in the base class and it will deduce the type, the static type of the derived class. And it will just work. Just like any other function template, you call, in this case, a member function on the self, which has been deduced. Notice neither of these classes are templates. And derivation is just normal class derivation. So no class templates, no recursion, just a plain pattern. Now imagine that we have a builder pattern. This is the case where you want to say .a, .b, .c, and the functions a and b return L-value ref so you can chain, and you have the classical builder pattern. What if you wanted to make a specialized builder that knows how to do extra stuff in that builder pattern? Well, with today's CRTP, we might do something like this. And there's some metaprogramming in here. You have to figure out whether you're actually working on the builder or the derived so that, you know, special.a can't return a builder ref because then it has to return a special ref because otherwise you couldn't chain together the C and D calls. And so you have to do this kind of conditional T dance or something like it, right? With, you know, if we want to go further and create a super special builder, then there's even more metaprogramming. You need to very carefully sort of reason about which of these classes is, you know, you need to figure out what to return so that you can chain together these methods. So we can chain A, B, and C, and D, and D, and E, and they all return the most derived type so that we can chain them all together. It's a bit of a wall of text. It's getting really complicated. With P0847, there's no class templates. It's just one flat pattern. You just say that self-deduction, you can add functions as you go, and it will all work because, again, of course, self will deduce to the most derived type statically known. And in all cases, that will be super, right, in this case. And so you can say super.a.c, and each time you'll get back the super ref because that's what was deduced. So CRTP really just, I guess, goes away and becomes this much simpler this much simpler thing with P0847. So, we have improvements. We get more functionality for less code because you can write getters and all that stuff, and with the deduction. You get more comprehensive functions because of it, because the very high likelihood today is that we're not writing all of these overloads. And very easy to accidentally sort of trigger one of those overloads and get a copy where you didn't want one or something like that. Well, now the compiler will make all those overloads for us because it's a function template. And CRTP now becomes much more layerable. We don't get that explosion of complexity, right? Anyone have any questions? Jody?
So in the previous one, where you had the inheritance, if it's a base class, if you did like a using my base class A, would it deduce the type for the drive class, or would you just bring it into the namespace? Just give you back the name.
Which slide are you referring to?
Yeah, so if it's special, you say using builder
If in special you said using builder : A, would it deduce to special or to builder? It would deduce special. It would deduce self always as what self actually is, the static type, the most derived type. So it would still be super. I don't particularly know a reason why, therefore, you would do using builder : but in this case. Yes, okay, I see. So some thoughts about access control and private and protected, etc. We'll get to a few of those things in the sort of miscellaneous section. Okay, so all these improvements are fantastic. I hope you agree. But fundamentally, they're not new. You can write them today, albeit with maybe some annoying copy-paste bugs and some cost to your sanity. And perhaps when we get, static reflection, maybe some of this will get a little bit easier, but that's some years away yet. Until then, at least, this is pretty cool. So now, let's have a look at perhaps what you're here for more, which is things that we can't write today, but P0847 makes possible. Well, if we're deducing the type of the object parameter, how about having it by value? Why does it have to be a reference? We can write member functions that deduce the type of the thing, and we can pass it by value. And this does exactly what you think it does. Less than here is an empty object. So we sort of actively want to pass it by value, right? Because that's very, very cheap or free, right? The compiler won't need to form a reference to it. And, this is true today of many, many small types. For example, non-capturing lambdas. And passing it by value is literally free. There's nothing to do because it's an empty object. So with P0847, we get this nice state of affairs. So yes, we actively want to do this for things that we tell people to pass by value, like string view. We can now pass by value to their own member functions, which we couldn't do before. Of course, it's unlikely we'll see this in the standard library because ABI, but we can dream. And we can certainly write it in our own code. So passing this by value also allows us to do things which today we can do with free functions, but not with member functions, like chains of move operations. And here's an example where we have a vector, and we want it sorted, and we want to just move the value through the computation, right? So we're taking the first parameter there, my vector, is the by value object parameter. And of course it moves into the value at the call site, and then RVO or copy elision, it must move out of the parameter again. Any questions? Probably several in the back. Sorry, I can't hear.
Oh, excuse me. Could we take questions to the mic so that we can have them available for the recording?
Can you move 2 slides back? Just
2 slides back.
Yeah. I mean, couldn't you easily do that today without this?
You can't do this with member functions today.
Okay.
Member functions will always receive their object parameter by reference today.
You just can do that with operator.
You can do it with free function operators, I guess.
Okay, I see.
But only certain operators are allowed to be free functions.
So
right?
it's just the fact that you're using
Yes,
per operator. Yeah. Okay.
This was an example using less than because I thought it'd be familiar, but this applies to any member function, and this is, member functions can't be by value today. Okay, where were we? Here's another example of where passing by value makes lifetime management a bit easier. So here's a coroutine that's just a generator that's yielding some values. And the lurking bug here is that there's a dangling thing. This is range 4, and we need the range 4 init, right? Which is relatively new in the language. This is not at all obvious. But if we write always to take its parameter by value, and in this case it's a const, but it's still by value, then there is no lifetime issue because we took it by value, right? Inside the function we have that object, and there is nothing to dangle on return. In this case, on co-yield. So, small example. So, again, you already know how this works. There's nothing special. It works just like any other function passed by value. Regular sort of C++ rules interact with it in a way that you expect. And we get better perf for small objects typically, which we now don't have to form a reference to and pass it. If they're empty, there is literally nothing to do passing by value. We get this new ability to move values through computations and through member functions without templates necessarily, right? And we get new options for lifetime safety inside functions with the ability to take things by value. So now we see how it solves my original problem. Inside the callback, I can write the lambda, right, with the implicit first parameter made explicit now. The self parameter is there, the this parameter, and I can say, hey, when I'm called, I want to forward the value along like my own value category. And so now I can move objects out of the lambda when it's safe to do so. When the closure object itself is an R value, I can treat its captured members like R values, and et cetera, et cetera. Okay. Now there's more simplifications that this gives us. As we talk through this feature, Gashper and I, we, over a course of a couple of days, we started finding all these things that it made simpler, and it was quite exciting. One of these things is considering Sphenae-friendly callable objects. This is something like what a not FN might look like today. So basically, there are a couple of operators here. One of them is on the const ref qualified, and the other is mutable ref qualified. They basically do the same thing. As you can see, there's duplication there. And and there's a sort of wrapper function that, or a maker function that returns the right thing. Now, the problem with this is, occurs when, and this is slightly esoteric, but pathological callable types can happen. For example, consider this callable type. We have two call operators, which are supposed to be const and non-const, but they have static asserts inside them, so they're not Sphenae friendly. And if you try to do anything moderately involved with metaprogramming, you'll know there are lots of Sphenae unfriendly things in the standard library. Anyway, when we try and call this, even though as humans we know which is the better match, the compiler has to instantiate both functions, and we get a hard error. So that's one type of pathological callable. Here's another type where we're trying to be a bit safer, and we are deleting the non-const form of the function. But even though that's the other one is a better match, or even though the other one's a better match, we want it to be deleted, the compiler will still do the wrong thing here because of the pathological nature of the callable object. And these kind of problems, you know, they don't occur in sort of regular code that I write every day, but they occur in spades in library code, and they're really difficult to solve right now, right? These kind of things are pathologically difficult to solve pre this paper. Well, with this paper, this is a complete implementation of not-fn. And I'm using boost HOF returns here just to avoid the you must write it 3 times problem, but that basically takes care of the trailing return type, no for Sphenae friendliness, no except clause, and the body. And we can write it as a lambda, right? And it just captures the function, forwarding capture. We have the explicit object pointer for the closure object, and we want to call the function, and all of the arguments get forwarded like, the function itself gets forwarded like the closure object, and the arguments get forwarded. Okay. Let's move on, because one of the exciting things here is lambdas. So, got a few things to cover here, and this might provoke some questions. What does this mean inside the lambda? Recursive Lambda expressions, who's excited about those? Quite a few people. Deriving from lambdas and overload sets, and a few caveats. So, one thing I'm going to try to do here, and I see Walter watching me, so I'm going to try and be quite rigorous, to distinguish carefully between the Lambda expression, which is the code that we write, right, and the closure object, which is the object the compiler generates by evaluating that Lambda expression, right? These are two separate things, and I will try to be precise. Even though I often just say, like we all say, I just say lambda every day just to mean either or both of these things. But mostly what we're talking here is about the value category of the closure object. So, you know, one thing to point out here is that uniformity of syntax was actually quite, between regular member functions and Lambda expressions, was sort of a major factor that decided on this syntax. One of the most common questions from people that we got in email who had read the proposal was, you know, did you consider this syntax, or did you consider this other syntax? And the answer is yes, we did. We considered, in particular, these 3 syntaxes here were sort of front runners at one time or another. They all have various problems. Alternative 1 makes this not a pointer, so that would have been dead in the water straight away. It would also interact poorly with lambdas that capture this. Alternative 2 has problems in parsing. C++ is complex enough that you actually, for many new features, need to find a sort of gap in the parsing code that you can fit it into, it turns out. Alternative 3 has issues with lambdas and possibly dependent type issues as well. So for all of these reasons, we chose the syntax that we did, which was sort of Hobson's choice in the end. So, as I mentioned, When you write this inside the Lambda expression, it still means what it always has. It means the captured this from outside of the Lambda expression. Now, in addition to that, you get to name the object parameter, which is the closure object of the Lambda. And you obviously can't name it this, because this is a keyword. So this still means the captured this. I can still be a bit sad that this capture I consider a sort of grandfathered in wart on Lambdas, but at least that won't break. So here's perhaps what some of you have been waiting for, a recursive Lambda. And of course I chose Fibonacci. Don't write Fibonacci this way. Look in EOP. So now what's happening here? We're getting the object parameter. The closure object is the first parameter here. It's this annotated. Notice it's by value, because why not? And we can call it inside the Lambda. We now have a name for it. We have a name for the closure object itself, right? In this case, we called it self, because I'm being conventional. But you can, just like any parameter, you can name it whatever you like. Now, this is fair enough, but you know, we don't write Fibonacci in everyday code. And it's always kind of the toy example. Here's a slightly more complex example that again elucidates something that's very important. Remember, type deduction will deduce the statically known most derived type, right? So here we're computing the number of leaves in a tree, and a tree is a variant of a leaf or a pointer to a subtree. And we make this overload set with overloaded, which you may have seen floating around. So what's happening here? When we visit this overload set, well, if we get a leaf, we just return 1. We're counting leaves. But this second Lambda here contained, the first parameter is deduced. So what type is that? It's not the type of the Lambda's closure object, because the most derived thing here is overloaded. Overloaded derives from all of the Lambdas that you pass it. And so the statically known most derived type is overloaded. So when we call visit self, we are visiting the overload set. Everyone clear? Any questions? So this is really cool. This is, you know, template deduction works as it always has, and it's a logical consequence of that that gives us this kind of power. So, with P0847, as I've mentioned, maybe we should think of non-capturing Lambdas conventionally. They should take their object parameter by value, because non-capturing Lambdas are going to be empty objects, and the compiler can optimize away that pass. And I think this achieves part of the same goal that the proposal for static operator print on Lambdas does. Not all of it, but I think this is a good thing. All right, I need to be a little more rigorous with Lambdas here and tell you about some caveats. So this, I imagine, is many people's mental model of Lambda expressions. When we write what's on top, the compiler generates what's on the bottom, approximately, give or take names, right? And if you go to CPP Insights, this is the kind of thing you see, right? How many people have been to CPP Insights? Yeah, about half the crowd. It's a great resource. So this is what we think of, right? The compiler generates this. Well, no, it doesn't, because there are some caveats with Lambda expressions. So what the standard says about closure objects says an implementation may define the closure object differently. And in particular, closure objects have none of these things. There's no defined layout. There's no defined size or alignment. There's no defined member initialization order. In particular, it's not the order you capture things in. In fact, there are no defined members at all. When you write members inside Lambda, you're not accessing variables. Those are aliases for something the compiler is allowed to munge, right? So, and this is by design, right? To give compilers freedom to maybe optimize things like taking one reference to a bunch of stack variables rather than multiple. As far as I'm aware, no compilers do this yet, but this is what the standard says. And for this reason, we're still fairly limited in what we can do inside Lambdas, even with the closure object parameter. So, but the things we can do are still very useful. We can basically do two things. We can ask for its type, or we can call it, right? Because it has a name. Things we can't do are access member variables, because those member variables, in a literal sense, do not exist, right? But, you know, there's no reason you would normally do that anyway. You would just use the alias just like a regular Lambda. So that's just a caveat on Lambda expressions and their closure objects. You can do two new things. Because it has a name, you can ask for the type of it, or you can call it. Okay, does anyone have questions at this stage? Yes, is that John?
If you access if you had a class with the
Please come to the mic, I can't hear you from back there.
If you had a class that derived from your Lambda, and it was the most derived, could you access the members of that class inside your Lambda? Like overload, like with overload, dot?
Yes, yes. So if there was a member variable in the derived type, then, and it derived from a Lambda, then yes, that class then has a layout. It's not a Lambda expression, just like our overload set. And yes, you could access public members of that class. Okay, in the time remaining, I want to go through a few miscellaneous things just to give you a flavor of some of these are esoterica, but it gives you a flavor of you know, what's required for standardization in some sense. So, we couldn't do this before. One of the things we couldn't do in the Lambda was constrain the value category of the closure object. This may be useful, not particularly with Lambdas perhaps, but with classes in general. This I think is going to become more useful. So in C++20, let's imagine that I want to write a class and I want to constrain the operator paren to only mutable L values, right? I don't want to call this on R values. I can't do this with a Lambda today. I have to write the regular kind of function object. With P0847, I can do this with a Lambda because I can constrain that L value ref to self. And these both result in compile errors. Now, oh, go ahead, Timo.
So I do have a question here. So I don't see like a theoretical reason why this should be a Lambda template, right? Like if you wouldn't have to write it like this with this feature, it could be just a regular Lambda, not a generic Lambda, right? So is there a problem with like the fact that it kind of becomes a template by virtue of just using this feature? Does that?
Well, I can't utter the type of a Lambda. So that's the reason it has to be auto, I think.
So you're making it a template just so you can utter the type. But otherwise there wouldn't be a reason to make it a template. Did I understand that correctly?
Yes.
Okay.
I guess you could say that.
Is that a problem or is that just fine?
I think it's just fine.
Okay. Thank you.
Right. So, as some of you may be thinking, anywhere we can put a template, we can put a concept. And with this paper, with this in the language, we can make methods that little bit safer, because we can say in our base classes, well, my object has to be regular in order to call this function, right? And at the moment, I don't think there's a way to do this, because you can't constrain really who derives from you. I mean, you get to say whether it's public or private or whatever, but you can't say that, you know, if you derive from me, you had better be a regular type in order to call this function. And now with P0847, we can do things like this. Because, again, wherever we can put a template, we can put a concept. Michael.
Does that just constrain that function call?
Does that only constrain that function call and not the entire derivation? So I can derive.
Does that only constrain? Yes, that only constrains that function template. Because, yeah, you can still derive and use every other method here, but if you tried to call that method and you weren't a regular type, then you would get a constraint concept error. Oh.
One other question?
Yes?
Could you do that on a destructor to prevent anybody from deriving it even if they don't call anything?
That's an interesting question. It isn't something I've tried. Try it in circle. There might not be a reason why not. So let's consider the template method, which is one of the classical design patterns from the Gang of Four book. In classical object-oriented style, it looks like this. You have your base and your template method, which, you know, your derived class implements. In more compile static style, with P0847, it might look like this. Instead of having the virtual functions to implement that method, you have a concept constrained method in your base class. And because it's concept constrained, we know that the derived type that comes in there is going to have those methods. And so we can do template methods like this now. And this is sort of morally equivalent to CRTP, right? So with this paper, the template method pattern is finally all of these things. We can simply express it, we can statically optimize it, we can safely constrain it, and we can appropriately encapsulate it. And we can use it generically. So we couldn't get all these properties before now because CRTP is not simple, virtual functions are not static, free functions are not the best encapsulation, and friend functions aren't generically callable, right? But with P0847, it's kind of exciting that we can get all these things. Now, a couple more things to cover. A method with an explicit object parameter behaves a bit more like a free function really than a member function. And this is why the name lookup changes a bit. So inside one of these functions, one of these methods, you named it, so you use it, right? You don't get to say this arrow I, or you don't get to say just I, but because you named the object parameter that comes in, you use that parameter. Now, there are a couple of things here where it can go wrong if you write ill-advised code. If you shadow a variable in a derived class that's in a base class, you're going to have probably a bad day. I mean, there are ways around it. You will have to explicitly use the syntax for looking at that member in the base class like this. Because again here, self will be deduced as a derived type. right? But we want to access I in the base, and so we have to write this kind of syntax. Hopefully it doesn't happen too much in code that you or I write. Here's another thing which is problematic. If you derive privately from the base, then it's a problem because, again, the self that comes into F is going to be a derived type, and there is no access because of that private inheritance. So this is bad behavior. And you're not going to like it, but this is the way around this is a regular old C-style cast, which ignores access. There are always ways to do things in C++. It's just, anyway, hopefully this doesn't occur much in your code either, and I hope it doesn't occur in mine. But these are the kind of things that you have to hunt down in standardization. You know, it's a sort of a window into the standardization process. All right, one more thing, another thing which, you know, might be more kind of what we want to deal with every day. Let's talk about pointers to member functions, because they change. So here is an example where new and old do the same thing. They are platonically the same thing, right? F and G, F is the old way where we've ref qualified the member function. G is the new way where we've given it that explicit object parameter. And we can call them s.f of 42 and s.g of 42. They will do the same thing. When we take a pointer to F, we get a member function pointer type, right? And we can call it with the member function with the dot star syntax, or we can call it by passing it to std invoke. That's true today. That's been true since C++ 98, I think. When we take a pointer to G, that is like a free function pointer, right? That is not really a member function pointer. That is now akin to a free function pointer, which, as you might expect, takes a const ref to S as its first parameter. And so you don't need to use the member function syntax to call it. Invoke still works the same way, right, as we might expect, but we don't need the dot star there. So, you know, I think this makes member function pointers easier to deal with, frankly. Member function pointers today are kind of something I don't like to deal with very much. Okay, so with this in the language, the question arises, let's adopt ADT style. Why don't we write all member functions this way? Why not always deduce this? And it's a fair question to ask. So I want to just run through some of the advantages and disadvantages of that. Well, we've covered a lot of the advantages. You get massive code deduplication and correctness by compiler, right? You get completeness by compiler. Anything you use, the compiler will synthesize from that function template. And if you're used to compile time polymorphism and writing templates, this is a pretty attractive option. Your class interface at least has the option to get sort of simpler and safer because you can constrain descendants using that function. You get simpler member function pointers. You get easier patterns like CRTP. And, you know, one argument is if you'll want it sometimes, you might want to be consistent and use it all the time. And finally, we think it's pretty teachable, right? The mental model for member functions is often, and many languages that aren't C++ make it explicit today, but it's often that there is that implicit first object parameter, right? So this is how we have a mental model of how it works under the hood anyway. So the advantages are pretty compelling for me. There are a few disadvantages. First is it involves putting in templates, and so there is a certain amount of implementation complexity there. We saw things like T and forward like T, and you know, when you have to use those things, that's a little bit more complex. It may also result in a little bit higher compile times. But you know, the trade-off there is you get that completeness and correctness. The other slight disadvantage is that deduction, you get the whole enchilada, right? The compiler deduces the thing, and maybe you just wanted to know whether it was const or not. But the compiler can't tell you just that. You get the whole type, and so you have to deal with the whole thing, right? There's no sort of semi-deduction just to tell you whether it's const or not. And of course, there are still some limitations. Deducing this methods can't be virtual yet. We'll see. So, is this good or bad? It's for you to decide whether you want to use always deducing this style or not. The other thing is that, as we've mentioned, you don't get to say this or implicit member access in deducing this methods. And whether you think this is good or bad is up to you. There's a bit more to type. You have to name that object. On the other hand, if you write a lot of template code, as I do, quite often you get tripped up with whether base type is dependent, and you have to write this arrow member quite a lot anyway. To anyone who's experienced that, this gets simpler. So, in conclusion, as I hope I've sort of explained and you're thinking, this ends up being a relatively small addition to the language. It mostly works as you would expect, and everything you know about C++ today, if you think about it sort of combining logically with this feature, it turns out the way you think it turns out. It's going to give us lots more easy things, especially in library code. It's going to give us some new patterns, and I've shown you some here, and these are just the ones that I've managed to think of so far. I'm sure this isn't all of the patterns that this will enable. Thanks very much to Sean. You can try this today at circle.godbolt.org. That's the paper, which is, as I say, in C++ 23 today, P0847. I'd like to thank my co-authors. And I'd like to thank you for listening to my talk. Now, questions. I know there will be some. Okay, David.
Yeah. So in those last slides, you're talking about the deducing this patterns.
Yeah.
Like pros and cons. Do you have a term for using the feature but not with deduction? So you would say this concrete. Right.
I don't have a term for it. If a term arises, then that we can all use, then. But yeah, you're right. I mean, I've talked a lot about the deducing cases because they're the cases that needed explanation. But the ability to constrain or just make the new way the same as the current ref qualified way is also important.
And the second thing I wanted to say was earlier there was a question about destructors.
Mm-hmm.
I'm assuming that it's specified to not work with destructors because it can't work with destructors. Because the static type, when you're destroying the object, is the base type.
Oh, that's right.
The derived type no longer exists.
Yes. Inside destructors and constructors, your type is your type. Yes, that's true. Jody.
Yeah, so first, I want to say, man, that was a great talk, and I think I'm going to go vote for you for a bobblehead because I loved it. You guys know I haven't really been the gangbuster for all the new features that have been coming through. But man, I'm head over heels over this thing. And we have two questions. Number one, since those functions are actually normal function pointers, does that mean that they would not be member function pointer? They wouldn't be member function pointers at all? They'd be regular function pointers?
Correct. They're regular function pointers, yes.
And so, interesting.
Which is great, right? Because member function pointers are horrible. I hate dealing with them.
It's great, but they're declared as member functions, but they're not seen that way. Yeah. So you could basically use them as just a C function to something that just takes some callable function pointer. Okay. But they still do have their access. So my second question is, when you pass this as a copy, what happens with the ref qualifiers? Because if I've taken something as a copy, then does that or if I take it as just a reference, does that implicitly
cement what the ref qualifier is? And so can you not put ref qualifiers on these things because they're implicitly part of the first type?
Right. You can't put ref qualifiers on these new functions. It wouldn't make sense, as you kind of intuited.
Yeah, okay, yeah. All right, thank you very much.
Hey,
Cameron.
I'm going to kind of play off that question a little bit. I was going to ask the function pointer question, but I have a slightly different question, which is related to the wording in the actual paper. And it might sound like
I may or may not be able to answer about wording.
The way it's specified is that it is specified as a member function. But
yes.
So the type to me would mean that it would be a member function type. But it's not a member function type.
The type is not a so probably it's worded as a member function because the access still applies, right? If the function is in the base class, the access privileges of the base class apply, right?
The same thing.
It is a member function of the base class. It's just that the pointer type is different.
But the same is true for like static member functions. But I think
yes.
that word is chosen specifically for overload resolution purposes. So as far as teachability, it's a little weird to have like a non-static member function that has sort of a static function type.
Okay.
Yeah. That was an observation. More.
Okay. Thank you. John?
Hey, Ben. Great talk. I was curious if in ADT style, by specifying always either a value or a reference, you anticipate pessimization of any potential optimizations that might be available were you to not specify in certain cases in the future?
The feature is too new. Obviously, I'm not using this in any sort of production way yet because it's only available on Compiler Explorer with Circle. So I can't think of any pessimizations that would occur with deduction. But it's very new. So
cool. Thank you.
I'm hoping everyone can figure that out. All right. Thank you very much.